Elasticity of solids, or what might be called deformation of solids, going to be the topic of this lesson in my brand new general physics playlist, which when completed will cover a full year of university algebra-based physics. Now in this lesson we're going to go through three different examples of the elasticity of solids. We're going to talk about stretching and compression with Young's modulus, we're going to talk about shear deformation with the shear modulus, and then we're going to talk about volume deformation with the bulk modulus. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So before we dive into the elasticity of solids, so a little quick reminder of Hooke's law for springs. And so we had F equals negative kx, where F was force, x was the displacement, and k was the spring constant. So it turns out that the force, the restoring force, and the displacement were directly proportional. If you double the displacement away from equilibrium for that spring, it doubles the restoring force pulling it in the opposite direction. And those are directly proportional, and the proportionality constant was that spring constant. And a larger spring constant we associated with a stiffer spring, one that was more resistant to getting a displacement, if you will. All right, well, in the context of the elasticity of solids here, instead of a force, we're going to be talking about what we call a stress. And instead of a displacement, we're going to be talking about what we refer to as a strain. And then the proportionality constant is going to be what we call the modulus, or elastic modulus. And for the three different types we'll talk about, there'll be a different type of elastic modulus for each. So we'll talk about stretching and compression, we'll talk about shear deformation, and we'll talk about volume deformation. And we'll start with stretching or compression. Say you hung something heavy from a rope. What you'd find out is that rope would actually stretch and get a little bit longer. So that'd be an example of the stretching. On the compression side, oftentimes you're going to have like columns being used as supports in buildings, like in ancient Greece. But even in modern times and things of the sort. And so the entire building above those columns rests down on those columns, and you'll find out that those columns actually get a little bit shorter as a result, and that would be an example of the compression. So if we take a look at what we call the stress here, it's not simply a force, it's a force applied across an area. So in the case of stretching a rope or a wire, it would be the cross-sectional area of that rope or wire. Often, those are cylindrical in shape, and so that cross-sectional area would be the shape of a circle. And so the stress is not simply the force, but the force per unit area. Now before you'd be like, hey Chad, I learned that force over area a little bit ago was pressure. Well again, this is technically not what we're going to refer to as pressure. So pressure is always a pushing force, and again, this might be a stretching force, not the same. So we're not calling it pressure in this case, it's force per unit area, but it is what we're calling stress in this lesson. It'll be analogous to force in Hooke's law, but instead of, again, a force causing a displacement, the stress is going to cause a strain. And ultimately what that strain is going to be in this case is a change in the length of that wire or the column or something like that relative to the absolute length of that wire or column. And we call this the fractional change in the length of this solid. And then the proportionality constant, again, is not a spring constant in this case, but it turns out for stretching and compression, that proportionality constant we call the Young's modulus. So the elastic modulus specifically in this case is the Young's modulus. And there's our lovely equation. So stress is equal to a proportionality constant, the Young's modulus, times the strain. And now we've defined all our variables. And so basically it's a little more complicated than Hooke's law and stuff like that, where we only had 3 variables. We've got more variables here, but it's still simply probably going to be some sort of plug and chug type situation. So in fact, before we move on to the shear deformation or the volume deformation, we're going to do an example of our stretching compression here. So a 10.0 kilogram load is hung from a 100.0 centimeter length of wire of radius 1.0 millimeters, resulting in an elongation of 0.50 millimeters. What is the stress, strain, and Young's modulus of the wire? So we'll start with that stress. And so in this case, we want force per unit area as the stress. So in fact, why don't we do this off to the side here? So force per unit area And so in this case, we're hanging a 10 kilogram load from this length of wire. So a 10 kilogram load, that's where the force is coming from, and it's going to be the weight hanging from that wire. And so in this case, that's going to be the 10.0 kilograms times gravity, 9.8 meters per second squared. So, but then it's across the cross-sectional area of this wire. Now we're given its length, which is not helpful in that regard, but we're given its radius. And again, the cross-sectional area of a typical wire is that of a circle, pi r squared. And the radius was given as 1.0 millimeters. So we're going to write that as 0.0010 meters. And don't forget to square it for pi r squared, the cross-sectional area of a circle. So, and ultimately that is going to give us our stress here. We'll let our calculator do the work. So in this case, 10 times 9.8, you can probably do that in your head as 98, but divided by pi, and I'll put this all in parentheses, pi times 0.001 squared, and we're going to get a really large number here. So in this case, your stress, the force per unit area, so, and if we do this in 3 sig figs, is going to be 3.12 times 10 to the 1, 2, 3, 4, 5, 6, 7th. So, and if you look at your units, it's newtons per meter squared. Newtons for force, meters squared for area. Okay, so there's our stress. First question answered. So the next question was going to be, what is the strain? And the strain, again, in the case of stretching and compression, is just the fractional change in the length. So if you notice, it's always the change in the length divided by the length. And so if it's a 5% change, this fraction is going to come out to 0.05, that sort of thing. So just the fractional form of a percentage, if you will. And so in this question, we're told that the length is going to change by 0.5 millimeters. And so in this case, if we look at delta L over L, so 0.5 millimeters is going to be 0.0005 meters. So and then we're told that the length of wire was 100.0 centimeters, which in this case would be 1.000 meters. All right, so I put it both in meters here, but notice the units are going to cancel. So as long as we use the same units either way, it wouldn't make a difference. All right, so we'll let our calculator do, actually, let's let our calculator do this for us, right? Anything divided by 1 is itself, and so that fractional change of length simply is 0.0005. And then we got to calculate Young's modulus, and we're going to do that by simply plugging this all back into our equation here. And so F over A, our stress, 3.12 times 10 to the 7th. And again, that's newtons per meter squared. It's equal to our Young's modulus we want to solve for, times 0.0050. And notice there's no units on that fractional change of length. It's length divided by length. And so it's got no units, which means your Young's modulus is going to have units the same as your stress, newtons per meter squared. And so in this case, we'll take that answer. The 3.12 times 10 to the 7th, we'll divide by 0.0005, and we'll get a really, really large number here. And so in this case, the 3 sig figs is going to be 6.24 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the 10th newtons per meter squared. So there's our Young's modulus, there was our stress, and there was our strain. All right, so now we'll move on to talking about shear deformation and the shear modulus. And almost always we use a nice big fat book to kind of demo this. And fortunately I have a CRC Handbook of Chemistry and Physics, and if you know what this is, it means that, like me, you're likely old. So we used to force students to look up all the chemical and physical properties and dangers associated with any chemical they might use in a lab and write it all up in their pre-labs and stuff like that, and now we have the internet. So these are kind of obsolete, except for it makes a good demo here, so good thing it's on my shelf. And the way this works, though, is I'm going to have this sitting flat on my hand, and I'm going to apply a force parallel to that top face. And my hand, there's going to be friction between the book and my hand that's going to hold the bottom part in place. And there's a deformation. And we say that this top face here, so in that dimension, has been sheared in this case. So let's take a look at what this looks like and how we define some terms. So here's what it looks like before we've applied the stress. So, and here's what it looks like after we've applied that stress from a side view here. So, and again, it's this top face, bottom face, that dimension that has been sheared. Well, the degree to which it has been deformed, that right there, if we kind of, that is delta x we'll define. And then the perpendicular dimension, that is going to be the height. That'll be part of our equation here in just a little bit. So, and again, as I applied this, I applied the force per unit area to that top face, and it's this area that's going to show up in our equation as part of our stress in just a minute. So it's the one that, the area of the parallel face to which the force is being applied. All right, so in this case, we're going to have a stress that is once again force per unit area. So, and just keep in mind, it's not the area of the side here or of this side here, but of that top face to which the forces are parallel to. It's that area of that face. And in this case, that's the stress. The strain on the other side is going to be the shear deformation. That, in this case, the parallel face that's being sheared. How much does it actually change by relative to the height of the perpendicular dimension there? All right, and then finally, the modulus here is our shear modulus. And once again, we see that, like we saw with Young's modulus here and stuff like that, Young's modulus is going to have units of force per unit area because delta L over L is going to be unitless as a fraction. Same thing here. Delta X is unit of length, height is unit of length, and so length over length will have no units as a fraction. And so the shear modulus will have units of newtons per meter squared. All right, so this is the one that students struggle the most with seeing is, where's delta X? What's H? Which area are we talking about? All those sorts of things. So let's take a look at a question here. So, all right, we've got to draw something here. Let me get this drawing up on the board. All right, so this diagram is right on the study guide, so I'm not expecting you just from the words alone to be able to draw this. This is part of the question. So a 60.0 kilogram man is forced to walk the plank on a board nailed to a ship extending 2 meters. So over the side, if the board is 20 centimeters wide, so and 5 centimeters thick, and drops 2.0 centimeters. So in this case, it bends a total displacement of 2.0 centimeters when the man stands on its end. What is the stress, strain, and shear modulus of the board? So similar from this point afterwards. So in this case, if we take a look at that man right there, so his force that he's applying here is a downward force, and it is, in this case, parallel to that face right there. That face is this end face here, so that is 20 centimeters in one dimension by 5 centimeters in the other dimension, so we know which dimensions we need to get the area, but it's the area of that face right there that we actually want when we're calculating out the stress here. And so we want the force per unit area. Well, the force that's being applied is simply the weight of that man. And so in this case, that force per unit area, so force is the 60 kilograms times gravity, 9.8 meters per second squared, that's his weight. So, and then the area here. So in this case, it's 20 centimeters by 5 centimeters for that face that we're parallel to in this case. And we should definitely convert that to meters. So 20 centimeters is going to be 0.2 meters. So whereas 5 centimeters is 0.05 meters. And I'm going to actually write it just like that. So 0.2 meters times 0.05 meters. And that's going to get us our force per unit area, and we'll let our calculator give us our stress there. And so in this case, 60 times 9.8 divided by 0.2 times 0.05. And we're going to get 58,800 newtons per meter squared. Okay, so there's our stress. Next part is to find the strain. And again, the strain, this idea of delta X over H. And in this case, we're turning everything. Instead of having a horizontal force, we now have got a vertical force. And so delta X here is how much the parallel surface is actually being displaced. In this case, that 2.0 centimeters. So, and then the H here is the perpendicular dimension, which is the 2 meter long board. So from that case, and so if we look at delta X over H, we're going to get, again, that 2 centimeters, which I'll convert to meters, so 0.02 meters. So, and then divided by the perpendicular dimension of the board, in this case 2 meters. So we'll let our calculator do the work here, but might be likely something you can do in your head. So 0.02 divided by 2 is going to give us 0.01. And again, this is unitless because it's length over length. So, but here we've got now the stress and the strain, and now we can use our lovely equation to calculate out that shear modulus. And so we've got the 58,800 newtons per meter squared equals that shear modulus times that strain of 0.010. So dividing by 0.01 is the same thing as multiplying by 100. So we'll just tack on a couple more zeros here, and we'll see that the shear modulus is equal to 5880000. Put a couple commas in there. Newton per meter squared. And it looks like we want 2 sig figs. So we'll round this, and I'll put it in scientific notation here. 5.9 times 10 to the 1, 2, 3, 4, 5, 6. 10 to the 6th newtons per meter squared. And we've now answered all the questions. We got the shear modulus, we got the strain, and we got the stress. Good to go. So the last example we're going to look at here we call volume deformation. And in the world of chemistry, we like to say that solids and liquids are largely incompressible. And if we use that word largely in front, it means not completely, but mostly. And what we really mean is that compared to a gas, yeah, solids and liquids are largely incompressible. So when you apply a pressure to a gas, you get big volume reductions. So often proportional up to certain points and stuff like that, up to certain limits. So, but for solids and liquids, you can undergo big pressure increases and only get very tiny volume decreases as a result. And so in comparison to gases, yeah, they're largely incompressible. But in this lesson, we're going to account for that teeny bit of compressibility in a solid. That's what we're talking about here with this volume deformation. So, and first talk about the stress. And in this case, the stress is not going to be a force per unit area. It actually is going to be a change in pressure. So oftentimes we like to look at this in the context of dropping something down into the ocean, and as it goes further and further down in the ocean, we learned that the pressure goes up, and that's going to be a positive delta P, a pressure increase in such cases. And what we'll find out is that as the pressure goes higher and higher, that solid object is going to decrease its volume ever so slightly. And so the corresponding strain here is going to be the fractional change in the volume. And it's going to be how much the volume changes relative to its original volume. You might look at this as being kind of analogous to taking a percentage, the percent volume change, except you're simply not multiplying by 100 to make it a percentage at the end. All right, and then the corresponding elastic modulus we call the bulk modulus with a capital B. So, and we only have one other problem before we can make this a perfect equality, and we have to put a negative sign in front here. And the idea is that as the pressure as pressure goes up, delta P is positive, that's going to correspond to a negative delta V, a volume decrease. And so delta P and delta V aren't directly proportional, only because one's positive while the other is negative. That's why we need the negative sign right there. Let's take a look at a question. All right, question on the study guide says, a solid metal sphere with a bulk modulus of 1 times 10 to the 11th Pascal. So now this has units not of newtons per meter squared, but of actual pascals, as we'll see. And notice, I realize a pascal is a newton per meter squared, but we'll call it a pascal in this case. All right, so a solid metal sphere with a bulk modulus of 1 times 10 to the 11th Pascal is dropped into a deep ocean trench where it experiences an increase in pressure of 1 times 10 to the 8th Pascal. What is the fractional change in the volume of this metal sphere? All right, so effectively we're given the bulk modulus, we're given the stress, which in this case simply is that change in pressure, and we want to calculate the fractional change in the volume. So a little bit easier calculation, a little bit easier setup than the other ones we saw here. So in this case, we'll just plug it in right below. So change in pressure was 1 times 10 to the 8th Pascal. Bulk modulus was 1 times 10 to the 11th Pascal. And we just want to solve for delta V over V naught. So if we were given the original volume, we could just solve for delta V, but in this case we're not, and we're just looking for that fractional change in the volume. So you should be under the impression that this ratio, this fraction, is called the fractional change of the volume, and we'll solve for it. In this case, we can probably do this in our head. So 1 times 10 to the 8th divided by 1 times 10 to the 11th is going to be 1 times 10 to the negative 3. And again, that is unitless. Change in volume would have units of volume like meters cubed, and the original volume would have units of volume like meters cubed. And meters cubed over meter cubed means no units. And in this case, actually, I should have given it one more sig fig to be in line with the numbers in the problem. So 1.0 times 10 to the minus 3 would be that fractional change in the volume. This would correspond to a 0.1% decrease in the volume. If you found this lesson helpful, consider giving it a like. Happy studying.